That should go pretty soon. Because like my here goes.
I was just going to ask you actually if you got Yeah, I did it. I asked her some questions about it. Mostly like it's no coding, it's just like it's just like
All right, good afternoon, everyone. Let's get started. All right, so we're starting week 7. So first, a couple of reminders. The homework 3, right? So it has been posted, separate ones for undergrad, grad sections. Okay, it's due this Thursday before class. Okay, so make sure you submit by the deadline. Okay. Also for this Thursday's office hour, my office hour, so it was scheduled for 11 to 12, but I had like one-time conflict, so I have to move it to Wednesday 4 to 5. This one is Zoom only, so hopefully you can make it if you have questions. If you cannot make this one, you need to talk to me. Please contact me, so hopefully we can find some other time to talk. Okay. So please know that this is for this week only. Okay. All right, so we have been kind of like reminding people, right, about the schedule of the class, right? So we are in week 7, so homework 3 is due this Thursday. Look at the next few weeks. Homework 4 will be posted this week, due next week, so that's week 8, right? Homework 5 is out on the 8th, week 8, and then due on week 9, okay? And then that'll get us to week 10. That is where we're going to have the midterm exam, okay? So what we typically do is that, like here, this is actually the week 9. We're going to have a midterm review. So we basically just go through the materials we have covered, okay? So we have covered a lot, right? So if you're like reading the textbook, you're already like feeling overwhelmed because the textbook has a lot more details, right? So we didn't cover everything in the textbook. And even for the ones we covered with different kind of details, right? So, we're going to use the midterm review to kind of guide you through, right? The materials we have covered, the ones we want you to understand and know how to utilize, right? So that you know what will be expected coming to the midterm exam, okay? Then after the midterm review, so what I'm going to do is I'm going to post the actual midterm exam we had from for 2022. So that was the last time I taught it, okay? So the idea is that like when you see the kind of questions, see what's being tested in that one, so that give you a sense of like what kind of things like we're trying to kind of like expect you to understand, okay? So some of you have been asking like, is it like calculation showing the steps of things, or is it conceptual? So it's like actually both, right? So there are knowledge that I want you to understand and be able to reason about, okay? There are also like concepts or techniques that we want you to know how to use, okay? So hopefully with the midterm review and also that example from the previous year, so you have a better sense of what to be prepared for the midterm exam. And then Thursday, October 31st, okay, that's the midterm exam itself, okay? So we plan to have it during class time, okay? So if you're in person, we should have a seat for you. A few of you, if you're in the like remote or online section, but would like to come in, take it in person, that's fine too. I think we should have space for some students from the online section. Okay, and then we know we have some students who need special accommodations, right? So we also just make sure in that survey we're going to send out sometime next week. Just make sure you fill out that information so we know like what your plan is, and if there's anything we need to coordinate, then we need to do that before the exam. Okay, all right. Any questions with the schedule for the next few weeks? Clear? All right, okay, so stay tuned, right? 2 more homeworks and the exam, okay. All right, in the previous lecture, we were kind of wrapping up our discussion about pattern mining, okay? So chapter 4, we will talk about the basic concepts of pattern mining, right? So generally we'll say, okay, how do you define a pattern being frequent, right? We particularly look at the frequent item sets, but then like when we move into chapter 5, we say, okay, there's actually a lot more, right? In the real world, there are all kinds of patterns you may be looking for, okay? So particularly we focus on the sequential patterns, subgraph patterns, right? Those are ones we kind of touch upon. We didn't get into details like of the techniques to do it, okay? But just knowing that if you have those kind of sequence data or like graph data in the real world, and if you want to find the frequent patterns, right? There are actually all kinds of ways for you to identify those patterns, okay? We then started the next one, okay, which is also a very fundamental concept and very important in data mining, okay? So there's also, of course, a lot of research in terms of general classification methods from the machine learning field as well, okay? But we are trying to use classification to determine, right, the class labels of different objects, okay? So the basic concept we're talking about is like, what do we mean by classification, right? So here you have training data, because you need some prior knowledge about how many classes are we talking about, right? Which classes are they, okay? And you need to give me some examples, right? So that is the kind of the training data you would need, and that's why like classification is referred to as the supervised learning, because you're being provided, right, with those kind of guidance, okay? We also talk about difference between classification and prediction, right? Because this generally just calls whether you have categorical class labels, right, versus numerical values. Okay, and then we'll talk about the difference, right? Supervised versus unsupervised learning, particularly like clustering, right? Which we're going to cover later in this class. Okay, so focus on classification, right? First, you need to understand the general process, right? You need a way to get the training data, train your model, okay, and then you can actually use your model for the actual test data, right? Very important. You should not be using any of your training data or your testing data for the training, right? Because the idea is that you should have clear separation. Your model shouldn't have seen any of the actual test cases. Okay, so we then start talking about one fundamental technique which has been widely used and has been shown to be quite effective in many cases, okay? So this is called decision tree induction, okay? So hopefully by now you kind of like, when I say decision tree, you can probably visualize, right? Basically, we want to take a training data set, right, where you have the like different instances with different attribute values, and then some class label, right? That's your training data. You want to then convert that into a tree, okay? So the tree is called a decision tree because basically you're using the tree by following the branches, right? You're trying to get to the leaf node. That's when you make a decision about the class label. Okay, so the high-level thing is about how do you construct the tree, right? It's a top-down approach, right? You start from the very top when you have the whole data set, and you're trying to use the branching conditions, right, to divide up your data set, such that when you get to a leaf node, right, the subsets, right, the subset of data points either have the same class label, you're done, right, or like you're done with all the attributes you can ask about, okay, or it's a majority voting, okay? But the high-level thing is that you go from the very top. Every time at each level, you ask one question about one attribute, okay? So that's the attribute selection piece, right? You choose this attribute, and then based on the attribute values, you have certain branching scenarios, right? So depending on the value of that attribute, then this particular instance would go to one branch, right? This should be only one branch for you to follow. And then when you get to the leaf node, that is when you make a decision, okay? So some of the benefits of a decision tree, of course, is that like you have actually a very clear way of explaining what your model is doing, right? How you come up to the decision, okay? Now, we talked about the information gain. So that was what we kind of were showing you as a actual calculation, right? So information gain is basically looking at like how your information in the data set is reducing, because information basically measures the kind of entropy, right? So it's basically how much variation you have in terms of class labels, okay? So at the beginning, you have a mixture of different class labels, and you're trying to use a certain attribute, right? And use the branching to have pure subsets, right? So pure subsets means that you're reducing the information in the data set, okay? So information gain basically says that you want to have the largest gain because you're reducing, right, the information, so that resulting subset is purer in terms of the class labels, okay? All right, but it turns out, right, if you just go with information gain, if you look at those cases, right, remember we were using, say, like customer ID, right? Customer ID is unique, right? If you use a customer ID, each ID has a unique value, then you would have basically the branch, each branch is for one customer. And within that one branch, you only have one data point. Apparently, that is the minimal information you have, right? Because it will be uniform, it's a uniform subset, which contains only one instance, okay? So if you just apply information gain, and if you have like attributes, right, that are like those kind of customer ID, product ID, that's kind of unique in your data set, then they will always pick those attributes from if you're using information gain, which is not helpful, right? As we have said, right? Your testing set will be different from your training set. So if you're using information gain and you have like customer ID, you would get a perfect classification, because once you have the customer ID, you can have the corresponding class label. But if you now have a new customer, you don't know what it can do, right? Because you don't have that value. Okay, so that's a problem. How do we handle it? Okay, so later on, people propose another approach. Okay, so using gain ratio. Okay, here the idea is that, okay, information gain, like when we pick those kind of like many branches, so meaning that I pick one attribute with a lot of values, right? That's not good. We don't want that. So we're basically trying to kind of like add in a term which we call as a split infer. So that's really is about how spread things are spread out. Okay, so you want them to be not too big of a spread, but it's smaller, right? So you're basically looking at, like, so now you have the D, which is the original data set, right? And now you have the D sub J, so that's the individual subsets, right, based on the value you have picked, okay? So now you want to actually have a way of saying, okay, I don't want that to be too spread out, okay? So this, again, is more like the entropy calculation, right? So you want them to be kind of a little bit more centralized or concentrated, okay? So once we add this term, then what we do is that we just take the gain, which is what we have from the information gain calculation, right? Divide it up by the split infer. So the idea is that if my gain is big, but I have a big spread here, right? And dividing by this as a denominator, then this value will be smaller compared to other ones, okay? But if you have a large gain and this split value is also small, that means you have a bit of concentrated, right, branching, then you will have overall a bigger gain ratio, and that is what we want, okay? So we want a bigger reduction in terms of information, but we also want them to be a more concentrated, because you don't want too many branches. That's basically the idea. There's actually one more, okay? So this one is called the Gini index, okay? What it's trying to do is doing the binary split, okay? Still like the similar idea, right? We're basically trying to like calculate a Gini index. We'll show that soon, okay? And then use a binary split. Still, we're trying to just reduce the impurity, because ultimately you want to have a pure subsets, right? That's when you can make your decision about the class label, okay? And then, of course, we're trying to reduce the impurity. So the larger reduction is what we want. Looks very similar, right, to information gain, but it has a slightly different calculations. This is called a Gini index, okay? So P sub I, that's basically just probability, right, of a class label happening in your data set, okay? Calculation, similar, right? Very similar to the information gain calculation, okay? But here, since I'm doing binary, right? Remember with the information gain, if you don't control it, it's basically one value per branch, right? Okay, so in this case, we would always do a binary split, okay? So the idea is you want to keep pick an attribute, divide it into two branches, such that you have a bit of kind of balanced like spreading, okay? And then the calculations are further, sorry. Okay, so we are looking for the largest delta, so the largest reduction, okay? But why do we have all the three different ones, right? We have information gain, we have the gain ratio, and we have the Gini index, okay? This is because they are all kind of focused on different things, right? Even though the high-level goal is the same. We're trying to take the original data set, which is a kind of mixed, like a mixture of the class labels, right? Has higher information, higher entropy, and ultimately want to get them to pure subsets, which has smaller entropy, smaller information, right? Almost zero, right? But when you define this differently, you will see that they're all generally good, okay? But in your data set, if you have attributes with certain properties, right, so that may or may not work well for certain like measures, okay? So it is an information gain, right? You have like an attribute with many values, right, a big spread, right? They will pick that, but that's actually not very helpful for your calculation, okay? While with the gain ratio, right, we basically say, okay, we want to have a more concentrated branching, okay? But that may end up with this unbalanced splits, because in this case now you want to have them more concentrated, right? So if you have a bit of kind of skewed like values, right, over this particular attribute, that actually may be considered good because you're using that split infer. Remember, the split infer is basically trying to look at like the concentration, right, more concentrated subsets. Okay, so Gini index, right, by using this binary thing, right, you tend to have a bit of more balanced split, okay, which is good, right? But since you're only doing the binary each time, it takes longer, right? Your tree then, like instead of having maybe a few branches at each level, now you have two branches, right? This is like a typical binary tree. So as a result, right, it may not be good if your number of classes is large, because that basically it takes a lot of binary splitting, searching to get to a subset or a branch that is pure enough, right, for you to make the class label decision, okay? So they just like, they're defined with different properties. Like again, as I said, like we have different measures. When you have your attributes, if you want to use a decision tree, take a closer look at your attributes and their attribute value distribution, right? So you can reason about how it's working out for your particular problem, okay? Because there are tools, right? Decision tree, like there are libraries, tools. You can just throw in your data, get a decision tree, right? But then when you look at the result, right, does it make sense, right? Other ways for you to improve it, or maybe select or remove certain attributes that wouldn't be useful, okay? All right, we mentioned overfitting earlier, right? So the idea with overfitting is that you're getting because remember you're provided with a training set, right? You're trying to train a model such that your model can be used for the unknown cases, okay? So you're trying to train a model that is kind of capturing some of the core properties without being too specific to the training set, right? Because sometimes some of the attribute or some attribute values may be too specific, right? So like if you're using extreme cases, like for example, like you may have instances of a very unique combination of certain values, okay? If you build a tree and using that as your branching conditions, you may be building like a very specific branching which may or may not, or actually sometimes may not apply to a more like general set. As a result, you have actually bad performance, right? Even though it works very well in the training set because you're kind of fitting, right, all the details. But those fitting of those details may actually restrict what you can do in a general setting, okay? So with the decision tree, that's the problem, right? Because remember, decision trees, like I ask more, like every time I ask a question, I get to some specific branch, okay? So it turns out that if your tree is too big or too specific, right, that'll usually have like good performance for the training set, but it is actually overfitting. Okay, so we want to prune the tree, right? So that means I don't need like all those different branches because some of those branches are too specific, okay? How do we do it? Either you do it prior, right, meaning that as you're building the tree, right, you stop at the point that like, well, it's good enough, right? I don't need like a 100% like purity, okay? Or you build up the whole tree and then you trim it down later, okay? So this is actually similar to like actual tree, right? Either as the tree is growing, you kind of restrict it in some way, okay, or prune it afterwards, okay? So here just the example, okay? So you have like, if you build the main full tree, this is what you probably get, okay? But in this case, for example, like in this case, right, I use the attribute 1, right? So that's A1, and I have a yes or no scenario. And then here I ask A3, have a yes or no, A5, yes or no, and then we have class B, class A, class B. Okay, so this one, right, this again is based on like the majority voting, right? Remember we're saying that when your subtree or the, excuse me, so when you have your subtree, right, ideally you want it to be pure, meaning that everybody has the same class label, right? But many times to get to that pure or same class label, you need to add many, many more layers, right? Which is not what we want, okay? So you want to stop when it's good enough, okay? So in this case, right, we don't have the actual number like showing the size of those, but like assuming like, so once you get to this subset, you actually already have class B being the majority, okay? That's when you can stop. Right, so instead of going further with all the sub-branches, we just say, okay, once like with this one step, okay, asking only one question about A1, I can already make a decision about the class label, okay? All right, so we have talked about decision tree, okay? So we'll be, of course, like doing some more exercise, right? We showed one in the previous previous class, so you will be practicing the homework about actually how to construct decision tree, okay? So hopefully you understand the process, right? You're choosing for each level, right? You need to compare across different attributes, but for you to decide which attribute is better, you're using one of those measures, right? Information gain ratio, Gini index, so that you can compute, right? Which attribute would give you the largest reduction, right, of the information. Okay, so that is one way to do it, right? And we have seen that it's reasonably easy to do, fairly efficient to do it, okay? And it's easy to use. Great. Okay, let's look at another approach. Okay, this one's called Bayesian classification. All right, so Bayesian classification is totally different, right? Even though they're trying to solve the same problem, meaning that I'm trying to build a classifier, right? But the approach is very different from the decision tree induction method, okay? So it's a statistical classifier, okay? So statistical basically we're saying we're looking at the probabilities, right? Because for me to determine whether this object belongs to class 1 or 2 or whatever, I'm calculating the probability or the likelihood, okay, of this object belonging to one of those individual classes. Once I have the probability calculated, then I just pick the highest probability, right? That's mostly likely for that particular label, okay? So you're trying to decide like a cat or dog or some other animals, right? So you're taking the different attributes of those animals, okay? And then you say, okay, given what I have learned so far, right, statistically, given those attribute values, right, what is the likelihood of this object or this animal belonging to one category? Okay, so the foundation is, well, the reason it's called a Bayesian classification is because we're using the Bayes theorem, okay? This is a fundamental, right, theorem. Probably you should have learned in the probabilities class, okay? It's the one particular thing is actually very interesting to note is that one, performance, right? Of course, we care about the performance, okay? So the good news is that it's comparable, okay, to decision tree, okay? And some of the neural network classifiers. So it does have actually pretty good performance, okay? And since it's a statistical, right, calculation, it's actually easy to compute. What's important is about this part being incremental, okay? Incremental is important because with the data mining, right, the set, if you have, say, one data set, and then you just construct one model, like one classifier, and you are done, great, right? But in many real-world cases, you have like a data that's being continuously being added, okay? Now the question is that when you have more data, okay, can you do this can you update your model in an incremental fashion, meaning that I don't need to go back to my previous data set to redo everything when I have more data. I can just update based on the new information, okay? So let's look at it, how this is incremental for the statistical calculations, right? Statistical calculation basically says that I'm calculating the probability, right? So if you already have, like based on your prior data set, you have calculated various probabilities about the things happening, okay? And now you have new data. You don't need to go back, right? You already have the probability calculated. You just need to update, right? So that's why it's incremental. What about decision tree method? Is that one incremental? Decision tree is a top-down approach, right? When I have the original data set, I construct my tree. At each level, I need to compute the branching scenarios and make a decision about which attribute to choose, right? Now, if I have more data, can I just update that tree with the new data I have? Yes or no? No, right? Because your decision is based on what you have done before, okay? Now, if you have new data, even at your top level, your calculations now may be different, right? And with the different values, then you may choose a completely different attribute, right? So first time you originally you're saying age is the most informative attribute, so I choose it as my top node, okay? But now with my new data, I say, no, it's not age, I actually want to use annual income. That one seems better, okay? Now, once you change that, everything below it need to be changed, right? Because your calculation is it's a recursive process, but now once you change the upper level, then the subsets, right, for your branches have all changed. So you cannot reuse, right, your previous branching. Let's say, oh, next one I'm going to use, say, the being a student or not. No, right? Because now everything has changed. So that's why Bayesian classification is particularly beneficial in many scenarios, especially when you're dealing with large amounts of kind of continuous data, incremental updates, right? This is actually a very important capability, okay? Now let's see how we do it. Okay, we said it's based on Bayes' theorem. Anybody still remember what the Bayes' theorem says? Probably no, okay. So I'll just write it out, okay? So generally, right, with the general idea is that, okay, I have a sample, right? I give you an object. It has certain attributes, okay? Now you need to determine the class, right? Okay, so here I have, say, X is a customer, right? Age, I have the age information, I have the income information. And then I need to determine the class label, right? So here, by the computer or not, okay? So in this case, I have two classes, right? Yes or no, okay? So what I want to do, of course, is to calculate the probability for each class scenarios, right? So giving the attributes, the attribute values of this particular customer, okay? What is the probability that this customer is going to purchase a computer, okay? Versus this customer will not purchase a computer, right? So that is what I'm trying to calculate. So if I written in the general form is what is the probability, right? H is my hypothesis. Hypothesis is about belonging to one of those labels, right? So the probability of X, so X has those values, right? Giving X, what is the probability that X belongs to H, or H, the hypothesis H is true, okay? That is what I need to do. And now you have a way of calculating what we call prior probability. Right, so that means it's not conditional, right? You can just calculate based on some statistical information in your data set, okay? So you can already calculate in my data set, right? What is the probability you see H? H is the class label. Like how often do you see your customers purchasing computer? How often they don't, right? And then you have the probability of X, so that means how often you see your customers having those attributes, okay? And then you can calculate, right, the posterior probability. Okay, so what we want, right, is this one. So giving X, what is the probability of H, right? But then you can also do it the other way. That means giving that, this customer, say, purchase a computer, right? What is the likelihood I would see this customer having those properties, okay? And that is really what we're going to leverage, right, with Bayes' theorem, okay? So the way we're doing it, right, what we want is this, right? This is what we need to calculate. Okay, But to calculate that, we can use Bayes' theorem because those other things I can calculate from my data set, right? Because in my data set, I can calculate, right, P of H, so how many people purchase computers, how many people have those properties, and also among the people who purchase a computer, how often you see those properties, right? So those are the things you can calculate. And with that, then you can calculate this one. And now you do that for different class labels, and you can pick the highest probability. Okay? So that's the process, okay? So let's look at like why this is useful and how this actually would be like applied in the real world setting. Okay, in this particular case, I think they're just trying to determine, like they were trying to do either playing golf or having a picnic, I forgot. But the idea is that, okay, I need to know the weather, right? If I want to do something outdoor, okay, I want to know whether it's going to rain or not, okay? So I don't know yet, right? Because I don't know whether it's going to rain or not later, but I have some knowledge. Say, okay, this morning is cloudy, right? We do that all the time, right? So now it's cloudy, then what's the probability that it will rain afterwards, okay? To figure that out, then you need to look at your history, right? So based on your like experience, right? How often do you see, right? How often see that it rains? How often do you see it's a cloudy day in the morning? And how often do you see when it's cloudy, it rains, and then when it rains, how often it's cloudy in the morning, right? So those are the scenarios, okay? So you can start calculating, right? So those are your statistical information based on your historical like understanding, right? So say 50% of all raining days start off cloudy, okay? That doesn't look too good, right? If we say half of them like they'll be cloudy. And then cloudy mornings are common. So that means 40% of the days start cloudy. Interesting, right? But then you'll say this is usually a dry month. That means like out of the 30 days in the month, only 3 of the days tend to be rainy. Great, right? So you can see, right, the different probabilities that we're talking about, okay? So if you look at each one of them, you have certain expectations. You say, okay, yeah, is it likely to rain or not? By using the Bayes theorem, right, which I like put it here again. So what are you trying to do, right? So knowing that, okay, this morning is cloudy, what is the probability that it's going to rain later today? Okay? And now what you do is, okay, use this, right? You basically say to calculate this, I just need to calculate the probability of rain, and then the probability of if it rain and then cloudy in the morning, right? Divided by the probability of being cloudy. That's the a priori properties, right? Versus the posterior probability here. If you plug all these numbers in, turns out, okay, if it's cloudy in the morning, there's a 12.5% chance of raining later, okay? So it turns out it's not that bad, right? So even though it's like say, well, the stars as cloudy, but based on my calculations, it's a smaller chance, right? Much smaller chance that actually it will be raining based on my statistical calculation, based on the historical information. Okay, are we clear? Because generally the idea is like how you work with the 4 different probabilities, right? These are the prior probabilities and the 2 posterior probabilities. They work together, okay? All right, now the question, okay, I know how Bayes theorem works and how I can use it for some, right, prediction. The question is how do I do it as a classification problem, right? So classifier, as I said, right, we need to decide the label, the class label, okay? So with the statistical calculation, it's really about which one has a higher probability, okay? So in my problem setting, I'll say I have X, that's my customer or my object, right? They have certain attributes, okay? And then you have certain class, different class labels, right? And you have the training data, okay? So your classification is about you want to find the maximal, so because you have a few different classes, right? You calculate the probability giving X the probability of any of the class labels being true, right? So you calculate all of that, pick the maximal one. Okay. And another thing you can notice already, right? Why I'm trying to choose between the different class labels, right? So C sub I is different. So you can see the denominator is dependent on which class I'm looking at. But the denominator, which is the probability of X, that doesn't change for the class labels, right? It's a constant. I don't know what it is, but it's a constant. So if you're now comparing, you want to choose the largest one, so I don't need to care about this denominator, right? Constant. It's the same value across the different class label scenarios. And for me to choose the one with the highest probability, I only need to calculate the denominator piece. Make sense? Just to make it easier, right? Okay, so once you have that, right, so you say, okay, I can ignore the P of X, so all I'm looking at is really this piece, right? The probability of a C sub I, so that's the prior probability of that particular class label occurring in your data set, right? And then say, okay, among, like when C sub I is the, like the class, how often do I see X, okay? There is actually one important property, okay? So when you look at your X usually have multiple attributes, right? So if you have multiple attributes, right? So for example, the probability of X given C sub I, you're really talking about each of the dimensions, right? So for each of the X sub K, so that means that like say age, annual income, or like which degree program they're in, which profession they're in, whatever, right? So you have a few dimensions, okay? So this is what we call, why it's called a naive Bayesian classified, because we're making this a naive assumption, okay? Remember, when you have multiple variables, right? The probability of the multiple variables having some combination of certain values, right? If you assume they're independent, okay, then their probability of them combined is actually the multiplication of their individual probability. Okay, so probability of A and B happening together, okay? If they're independent, that means it doesn't matter, okay? So then the combined probability is the same as the multiplication of their individual probability, okay? But we're making this assumption here, right? So if this assumption applies, then we can convert this, right? The combined X across different attributes. Now I can just do the multiplication of the individual attribute values, okay? Now you basically just write it out like this, right? So if you have n dimensions, then you have this n terms of posterior probabilities that you're trying to combine. Okay, so if you read this out, for example, like if for people who purchase computers, right? How often do you see them being in a particular age group? How often do you see them being student or not, right? How often do you see them like having a certain annual income or credit rating, right? Okay, and then you can calculate with your table, right? You basically just go to that particular attribute like column, right? And then count, okay? All right, and this is like if it's a categorical value, that's easy, right? We're already done, okay? So we just calculated the probability of the individual ones and then say, okay, with that, then high is the probability, okay? If it's a continuous values, okay, that's a little bit harder, right? Because it's not just the probability of this particular value happening. Rather, it's the likelihood, right? You're talking about the distribution, okay? So usually in this case, we assume this is a Gaussian distribution. So you actually turn into the Gaussian distribution with the two key parameters, right? One is the mean and also the sigma, okay? So that would then give you a way of calculating, right, the probability of X, right, that continued like a valued attribute having a particular value, okay? So if that's, for example, if you look at the class, right, if you have like your exam scores, right? So the chance of someone getting like a particular value like 93, right? But you don't just look at how often I see 93, right? You have 92, 94, 95. So you want to see the distribution, and then you have a way of like estimating the likelihood of having that particular value. Okay? All right, so putting all this together, now let's work on our table, same table that we use for the decision tree calculation, okay? Same thing, right? We say that, okay, we have two classes, right? Buying computer or not. These are the two, yes or no. And I have my like instance, right? So this particular customer, right? Age is at most 30, income is a median. This is a student, and credit rating is a fail. Okay, now we need to decide, right? We need to calculate the probability of this person purchasing a computer or not. Okay, to do that, right, we need our like the instances. Okay, so if you follow our process, we start with the prior probabilities, right? So that basically like each one happening. So out of my 14, okay, let me try to do this. So out of my 14 cases, I need to say, okay, how often do I see like purchasing computer versus not purchasing computers, right? So that's the prior probability. And then we need to do this, right, which need to be then spelled out, assuming independence across those attribute values. But here you can probably already note this, like usually your age, your income, credit rating are probably related, right? They're not completely like independent. Okay, so we'll see later how we deal with that. But it turns out in the real world usage, right, even sometimes you don't like have, say, 100% independence. When you apply this naive assumption, they still give you a reasonable classification performance, which is good. Okay, so in this case, right, we are breaking this apart. Okay, so say, okay, this is my customer, right, with those properties. So I basically need to break down age, income, student, and then credit rating. Okay, so that's what I need to calculate. Okay, so if you want to follow the process, okay, it's a lot to read. Okay, so I leave this for you to like do the actual calculation later. But if we're just like following the procedure, okay, so first one I said like I needed the class level, right? Class level like prior probability. Okay. So out of my 14 cases, 9 of them purchased computer, 5 of them didn't. So these are the buys computer, yes or no cases, right? First one. Then I need to calculate, right? When they buy computers or no, what's the likelihood of seeing a particular attribute value, right? Okay, so this is like a yes, buying a computer, age is at most 30, so that's the like conditional probability, like a posterior probability, right? Knowing that among the 9 people, right, 9 people who purchase a computer, how often do I see them having age at most 30? That you can calculate, okay? So you go to the table, you'll see, okay, out of the 9, I have 2 of them, okay? Similarly, right, not buying computer, I know I have 5 of them. And out of that 5, then you look at the age information and see, turns out that 3 of them are actually at most 30. That's how you do your calculation, okay? Now I need to do this for the other attributes, right? Income, student, credit rating. So for each one, I have the 2 class labels, okay? So that's why I have, let me see, 4, right? 4 attributes, and I have 2 classes. So here I'm calculating 8 scenarios, right? For each of the class label, each of the 4 attribute values, okay? Once you have that, now you need to combine them, right? So now giving that, like say, buying computer as a yes, and then what's the probability of seeing X, right? You just multiply, it's assuming the independence, right? So you're basically multiplying those probabilities together, okay? So if you do all this and then you calculate that, and now finally, right, using the Bayes theorem, so it's not about the posterior probability, but also you need to have the prior probability of each class label happening. So you need to combine these 2, right? So this multiplication for each of the 2 classes. And these are the final values I get, okay? In this particular case, which class label should I choose? Higher value or lower value? One is 0.028, one is 0.007. So will this person purchase a computer or not? Yes or no? Yes, okay, because a higher probability, right, for the yes class. Okay, all right. So this may sound a lot, right, if you have to do this manually, right, especially if you're doing the counting, right, this is actually the time-consuming part, okay. So manual process may be a little bit challenging, but if you have this written as the script, this is actually very simple calculation, right? All you're doing is going through your data set, counting the individual values for the different attributes, okay? Do the calculation, you have the probability calculated, and then it's actually a very simple process, okay? So there's one issue, right? Remember we're multiplying the probabilities, okay? And one thing with multiplication particularly is that whenever you have a 0 probability, everything becomes 0, right? because 0 means that that never happened, right? So if you had somehow in your calculations, like this student had like this customer had an attribute value that never occurred, right, in the data set, but you may see it in the new data, right? So in this case, you would get a 0 probability, and your overall calculation, right, would become 0. Okay, that's bad, right? So for example, if your data set, right, doesn't contain anything with like a low income, okay, but later on you are expected to work with somebody who may have low income, right? So your model still need to work with it, okay? So there are two kind of aspects to note. One, that's why I always talk about your data set need to be representative. Your data set need to have good coverage, right? Because whatever you're trying to train the model with, right, should be representative of what you will see, right, in the real world or like likely to be applied to, okay? So that's one scenario. If you have a good representative data set, right, you may not see this problem at all, okay? That's one. Second, if it happens, what do? Do you say, oh, I've never seen this. This is 0 probability. I cannot do anything. So I would just fail in this case. But one thing with the probability is this statistical calculation, right? It's actually very interesting, right? So 0 versus, let's say, other cases, for example, like the cases of low income is 0, medium income 990, high income is 10, okay? We just need a very small modification to turn that 0 value into something very small, okay, but non-zero, okay? Once it's non-zero, right, your calculation can still move along. You will have a very small value. So that means if when you compare, right, the probability, that would not, right, throw off your calculation or your comparison, okay? So it's basically a small adjustment, right, to avoid the 0 probability scenario, okay? Turns out very simple. What I do is that I just add 1 to each of them. Great, right? But as you can see, right, because if you once you add it and then you look at the relative probability, right, it's very similar to the original one. But now you don't have a 0 probability. Okay? All right. So let's summarize, right? Naive Bayesian classifier. So by now you know how it works, right? It's basically calculating, right, for the different class labels, the probability of seeing certain attribute values, right? So you can use the the Bayes theorem to calculate the prior probabilities and then the posterior probabilities across the different class labels and across the different attribute values, okay? Once you have that, you can just compare, right? Find the largest one. Okay, so advantage, it's very easy to compute, as we said, right? If you have some kind of automated tool, all you need to just go through your data set, count the occurrences of different scenarios, calculate the probability, right? And it has been shown to have very good results, actually, in many real-world cases, okay? Even when they are not exactly like independent, right? Remember, this is the naive assumption, right? But they still tend to have good performance. But there are a few disadvantages. Right? So what is saying, right? This is conditional independence. Sometimes it's so clear that they are dependent, right? You have two attributes, and you say that like they have like certain relationship. Okay. So we already mentioned earlier, like say your age, your income probably somehow related. It may also be related to the profession or the degree, the highest degree you have. Or like what kind of food you like. It also may be related somehow, like which region you come from or something, right? So there are certain things that maybe have some kind of like underlying, right, dependence, okay? Particularly, like, for example, in the like medical setting, right? A lot of times certain symptoms, right, or conditions, they're related, right? So if you just assume that they are independent, that actually would really throw off your calculation. Okay, so you need some way of kind of still capturing that dependence. Okay, and that is something we'll talk about later, right? Remember chapter 6, this is just basic concepts. Okay, but later on when we go to chapter 7, we'll talk about like ways to incorporate those kind of like dependence okay, in the Bayesian belief networks. So that actually kind of like specifically captures, right, dependence across certain attributes. Okay? But for now, right, we just say, okay, we have talked about basic concepts of what is a classification. We have shown two widely used approach, decision tree and a Bayesian classification. Okay? They have all been actually pretty good performance in many real-world settings, and they're easy to use. Okay? Next, we're going to talk about a couple more, okay, classifiers. First one is called lazy learners. It's interesting, right? When you look at the term, what does it mean? Okay, so the high-level thing is in terms of contrast, right? Eager learning versus lazy learning. Okay, what is it talking about? This is actually a little bit similar to earlier when we talk about the data cubes, right? We're talking about materialization. Okay, so the full materialization, right, versus like zero, right? So the idea is that how much upfront work you want to do. Okay. So eager learning means that, okay, you are always kind of on top of things. So when you get your training samples, you already kind of work hard, try to build a model, right? So that when you have the actual test cases, you can just apply your model, right? Great, okay? So in this case, you do some work up front, right? But then you can do less work, right, at the runtime. The lazy learning basically says that, I don't know, I'm going to wait, okay? So I get the data sets, right, the training samples. I'm just going to store them somewhere. So, okay, I got those. It's in my record. But I'm not building a model yet, okay? I'm going to wait. Wait when I actually see a query. Somebody's now asking me, right, okay, given this new data point, can you assign a label? Like, can you tell me the class label of this object? Now you can say, okay, oh yeah, okay, this is the query. Now let me go back to my training sample set, right? In this case, you're not necessarily trying to build a model, right? That'll take a lot of time. But more importantly, the assumption for the eager learning to build a model is that you have the knowledge, you have all the information, right, in your data set to build a model such that the model can be generalized for whatever would happen later. Okay? That may or may not be the case. Okay? So let me give you a concrete example. This is from my research project. Okay? So one research project we did, this was materials. Okay? So I'm working with material scientists. So they have different compounds, right? Like new different chemical compositions, and they're trying to build new materials with certain properties. Okay? So they have, I think, thousands of samples. Okay? But the challenge is that those compounds have many properties. Okay, I think we're dealing with 40-some dimensions. Okay, so we try to build a model because our goal is to find compounds that are likely to have certain kind of nice properties we're going after. Okay, so we try to build models using the thousands of existing compounds, and our model failed miserably. Okay? It just couldn't give us a good differential power about this is a good compound, that is not a good one. Okay? Turns out, right, I just don't have enough information because you think about it, right, it's a huge space. Okay? With all the new materials, right, what you can do with it, it's not just the chemical elements themselves, but also the various ways of doing it, or well, I'm not the expert there, but there are actually a lot of possible combinations, a huge space. So if you're trying to build a model using the data you have, it's not going to be a good model. And we actually realized later that it's not good, right? So we actually turn to the lazy learning approach, okay? So the idea is that, okay, I don't have all the information, right? I cannot give you a good, like a global model to tell you whether a new compound is good or not, okay? Instead, now you have a new compound. You say, okay, if I try this new compound, how will it perform? What I do, I go back to my thousands of samples. I try to find similar ones that look similar, right, in their properties, okay, compared to this new compound, okay? And in my training set, I already know, right, how those compounds perform, right? And then I say, okay, given this new compound, I go to my training set, find someone similar, and I know how well they're performing, and then I can say, okay, they all perform pretty well actually in those along those properties. So that actually may be what I'm going to give you as a class label. Make sense? So in this case, right, I'm not trying to build a global model, but I'm trying to use, right, the information that I have, and I'm doing a bit more like a local search. Make sense? I'm just finding things that are similar. Okay? So how many of you are, well, I'm not an expert, how many of you are familiar with the legal kind of domain? Like a lot of they use the cases, right? Historical cases. So if you're going to come up for a particular case, you go back to the history, you look for similar cases, right? And then say, okay, in those cases, that was the ruling, okay? And then you say, okay, you can use that as your support and say, okay, that's what they happened, they did there, and so you're using those as like a way to guide the new case. So that's what we're doing, right? So lazy learning said, I'm not doing any training. So I am spending a lot less time, right, at the training time. But of course, I need to do more at the runtime, okay? Also, I need to kind of manage, right, the instances, the training data more efficiently. Because if you are building a model, once you have the model, you don't need the training cases. The model by themselves is what you need, right? So with lazy learning, I need an efficient way to manage, right, those instances, so I can quickly find the ones that are similar. Okay? But also, more importantly, right, that's why we want lazy learning, is that we're not making assumptions up front. Okay? As a result, right, you can have like a lot more flexibility, and what they say is like a much richer hypothesis space, because I'm not making assumptions. I don't have a model yet, right? I just look at what you're looking for and then search my space to find what may be something that you can use. While with eager learning, right, you're trying to map the whole world, the whole space, okay? Which sometimes works, sometimes it's just not applicable. Okay, so to do that, there are different things, right? We already kind of mentioned some of the high-level idea about how you do it, okay? So generally, you're just trying to use the instances you have, okay? So that's what we call like instance-based learning, right? So you store those instances, right, which already have your class label, okay? And then once you have a new instance, you try to find ones that are similar. Okay, K nearest neighbor, as the name suggests, we're just finding neighbors, right? Based on some kind of similarity like measure, okay? So once you find them as similar, in this case, right, we typically, if it's numerical data, you use Euclidean space. So you can calculate, right, how similar things are, okay? This could be very useful if you have manageable dimensions, right? Remember, we're talking about dimensionality, like the cursive dimensionality. So this works well when you have smaller number of dimensions. Okay, but it's challenging when you have more dimensions. Okay, another one is about this called locally weighted regression. Okay, so regression meaning that like basically we're trying to fit right some data with a model's regression model. But if it's a local weighting, so that means you're actually trying to really look for in the local setting, right? How things can align with what you're looking for. So again, I'm not talking about the global fitting, right? I'm looking at, like, so given this instance, that's why it's also dependent. I cannot do it until I have the actual instance at the runtime, okay? So I use as an instance, I find things that are fitting better in the local setting. Okay, case-based reasoning. So that's what I say, like when you don't have numerical data, right, sometimes it's just hard for you to do some kind of numerical calculation to figure out the similarity, right? So a lot of times you need to look at some of the semantic, symbolic meaning so that you can identify, like, for example, like with the legal cases, it's like how certain cases are similar, right? They may not just be like say, a value, say how maybe the amount of the value of the, say, the cash or money that's involved, right? So instead, you need to have some kind of semantic meaning to allow you to define similarity and find the things that are similar. Okay, so here I'm just like illustrating a little bit, right, how you do the K nearest neighbor classification. So the idea is simple, right? You have your space. This is like the whole space. I don't have everything, but I have some training samples, right? And I have the labels. That's important, right? Because I need to know whether they're positive or negative, right? It's just there, okay? And once I have a like new instance, that's my query, okay? Now what I'm trying to do, I think this is the point, right? So you're using this point, so that's the value you're looking for, and then you draw some kind of like radius, or sometimes you just find the ones that, like either say they're within a certain radius or say the top k, right? So they're most similar, okay? So once you pull out those, and then you have their labels, and then you basically do some kind of majority voting. It's like, okay, I have say 5 like nearest neighbors, and then like 4 of them said positive, 1 of them said negative, right? So that's what you're going to do. Okay, yeah, then I'm going to say, okay, the label should be positive, okay? So in this case, right, it's simple, right? You basically just need a way of say how to calculate the distance, right, between the different points, okay? Another thing is that this is also why like this is the overhead, right? You need a way of indexing because the nearest neighbor search is actually challenging when you have large dimensions, okay? Sometimes it can be very slow, okay? So there have been actually a lot of research about like indexing high dimensional data for similarity search or k-nearest neighbor search. Okay, now there's another thing, right? We say k. How do you know like which k is good, okay? So at a high level, right, if you use a smaller k, so basically you have a tighter like neighborhood. Smaller k, that means, okay, you're looking for things that are very similar to you, right? That may be good, right? But sometimes that may be too specific, right? This gets to a little bit of the overfitting scenario. You're looking for things that are very similar to yourself, and you're not looking a little bit beyond, okay? So too specific. If you have a larger k, right, you may be including too many things that may or may not be relevant, okay? So again, using my like a new compound for the materials, right? So it's actually important for you to pick a sufficient space, right? So that you're looking for compounds that are somehow similar, of interest, but if you're just like including too many of them, they may be throwing off like your classification decision. Okay, so this is just a way of illustrating, right? Like if you have this basic k is a 3, 5, 117. Okay, so you can say like if you have a very specific k, like a larger k, you're including a lot of them, and now you have quite a bit of mixture, right? And now actually these two sides don't have a clear separation now. Okay. Well, if you have a very small one, then the idea is that you only look at the very close neighborhood, right? Like in this case, right, this actually majority is the red dots, but if you look at this very small neighborhood, you only see some of the blue dots, and you may use that as your guidance, okay? So this is all about just like the reasoning, right? But there's no, like say, like the best number because all scenarios are different. So that's why when you are looking at your data set for your application, if there are some kind of semantic meaning you can leverage so that you can pick, right, this more properly, that's good, right? Sometimes you probably need to just play with different values anyway, but just knowing like how you compare, right? Knowing that you need to at least look at how the different parameters may impact your performance. All right, so we talk about quite a few, right? Decision tree, Bayesian classifier, lazy learning, linear classifiers. Hopefully this one is something that we're more familiar with, right? We all have heard about regression, right? Linear regression, that's actually widely used, right? The high-level idea is that you're using kind of like a linear model, right, to fit your data set, right? So the simple case, right, would be this. I have like this one line trying to fit some data points, okay? Or you can have something that's a little more complicated, but generally the idea is that you're using like some model, okay? So this is usually this weighted vector or weight vector we're trying to get to, right? So you have your original data. This is your objects with, here we say p dimensions, okay? So x can be represented by those p dimensions, okay? And then you have the observed values, right? That's important. So one example I think here is that like, depending which area you live in, then you have the price of the house, okay? Or say you have the individual instances of like the age of a person and then the annual income, right? All those just dots once you plot it, right? Like points in this space, okay? And now you're trying to use some kind of a model, right, to fit it, okay? So what we're doing here is that you have some kind of really just this weighted sum of x, right? Because x is the p dimensions, that's what you have there. And then you have the weight vector has the same number of dimensions. That basically you're basically saying like one weight for each dimension, right? You sum them up, okay? And then you have this bias, b, so that's just some kind of offset, right? To then like allow you to like align your data. So ultimately, once you build the model, you have this two parameters, right? The weight vector and the bias. That's all you need. Okay, so linear regression is actually simple, right? But it's very powerful, right? It can be used in many real-world scenarios, okay? And the fact that it's actually easy to calculate, right? So generally, we use this kind of least square method, okay? All we're looking at is that it's the square, the sum of the squared difference, right? So this is the actual value for each case. This is the mean value, right? So you say, okay, what is this observed value and the actual, the calculated value. So you're basically trying to find this L, right? Find this weight vector and the bias such that, right, the sum of the squared sum of the differences is minimized, right? Close, right? Close fit. In this case, since this is actually linear regression, turns out there is a closed form solution, okay? So you don't need to memorize it, but basically you need to understand what they mean, right? For example, like what you're looking at is really the difference of you have the original for each data point, right? You have the value of x for each of the dimensions, okay? And then you're looking at the difference, right, between the weight vector, the multiplication of the weight vector and the actual x value, and this is the observed value. So the best case would be that everything fits, right? Then you would have 0. That's the smallest case, okay? But the way, as you're choosing between different weight vectors and bias combinations for your model, you're basically trying to look at the difference, right? The squared difference, and find the model with the smallest difference. Okay, so the textbook has some more details for this particular example, so you can follow the textbook to see how you do the calculation. Okay, nowadays, of course, the linear regression is standard function, right, in a lot of libraries. So you can probably just plug your data in and just see what you get. Okay, but I want you to at least understand the underlying mechanism, right? You're trying to fit the data, but you're just trying to look at the difference. Okay. All right, another one, logistic regression. This one is also widely used, right? And if you are paying attention to some of the kind of like neural network deep learning work, this is actually widely used, okay? It has actually very nice property, right? So the main thing is this is sigmoid function, right? So basically it's differentiable. This is important, okay? So what it's trying to do is that I'm taking whatever value, right, you may have, and then project it into this 0 or 1 case, right? Or just a value between 0 and 1. That's a probability, okay? But one important thing is that this projected value changes sharply around the 0 point. So that means, remember we're doing classification, right? So on one side is 0, another side is 1. So as you look at this value, right, what do we say? The probability of a snow, let's say, right? Precipitation, okay? So you look at quite a few things and you project into some kind of value and then say, okay, if you're seeing the combination of a certain value, but at a certain point, it gets to the threshold, right? If you're on this side, then the chance of snowing is much higher. Below it, then you actually have a smaller one, okay? So that's the high level idea, okay? Because of this nice property, right, we actually can then find the best regression, logistic regression model. But here, what we're finding is this weight, right, against the weight vector that we're trying to get. So it's called a maximum likelihood estimation. Okay, so this is basically, again, no need to memorize the formula. Okay, but the high-level idea is that you're finding a vector, the weight vector, that'll give you the probability that is most likely for you to be able to reproduce or like similar to the data you have observed, right? That's the idea, right? Because you're being provided with the sample set, right? And now you're trying to fit things such that the probability for you to see the original data set is maximal. Okay? How do we do that? Okay? So you may have heard this term about a gradient descent. Okay? So the idea is simple. Okay? So gradient descent, you basically like you follow somewhere, and then you basically keep moving along certain direction, and this is the gradient, right? So basically the way, the direction, or the wave that the things are changing in one direction or other, and then you're trying to get it closer. Okay, and in this case, it's a descent. That means you're trying to reduce, right, the cost until you get to a local minimum. Okay, earlier we talked about you want to maximize the likelihood, right? But the reverse of it is the negative log likelihood. So if you take a log of the original term, right, you will say, okay, if I minimize the negative log likelihood, it is equivalent of maximizing the likelihood. Okay? All right, so I have a few illustrations. Again, I said that no need to memorize all this, but I want you to understand what we're trying to do, okay? So when you're doing this, likelihood, what you're looking for is that how do I change, right? Because I start at some point, okay? And as I change it, as I adjust the things, okay, I have different directions to make my next adjustment, right? So right now, we'll say we'll look at the gradient. So that means that from the previous point and here, so I have this potential direction I can go. But then what I'm trying to do is I'm trying to get it closer, right, to the example I have. So there are two cases. One is that this is actually a positive case. Positive means that is what I'm looking for, right? So I want to be able to match it or get closer to it, okay? So if you look at the illustration, right, so this is my original, or my current, a weight vector, okay? And this is the x, okay? So if it's a positive case, now I'm trying to pull it closer, right? So you can see, right, my new weight vector, I want to adjust it in a way such that now I'm getting closer to this one, okay? If it's the negative case, I want to move away, right? So I mean, wrong direction, I need to go the other way, right? Okay, so in this case, right, if it's the label is the 0 case, okay, that means that, okay, I want to actually minus this change. So that means I want to move away, okay? So same thing, the old vector, this is the x you have, and now you're trying to move away. So in this case, right, as you can see, using this calculation, the effect is basically now I'm further away. Okay, so in the earlier case, you try to get closer to this side, and now you're away from it. Okay, so there's a lot more, of course, mathematical calculation, but at a high level, as I said, this process, right, is that I'm trying to find the vector, the weight vector, right, that allow me to have the highest probability, right, of matching the original sample set. Okay. When making the adjustment, right, if it's a positive case, I move closer, right, to the alpha times x sub I, so that means move closer to that sample. Okay, if it's a negative case, that means, okay, it's different. I should go the other way. Okay, so that's a high-level thing. And with a gradient descent, it's an iterative process, right? You keep doing it, okay? So usually, there's another key factor that's about the stride or learning rate, okay? So that's about how quickly you want to make changes, right? So the general idea is that if you use the same stride, okay, you may actually miss out, right? Some of the better scenarios, because as you get closer, right, to the optimal solution, you actually want to use a little bit kind of finer steps, right? And also there are scenarios where say you may what did I say? Oh, for example, we did this for recommender systems. We actually find that when you have big mistakes, right? So do you actually can adjust your learning rate, right? Big mistakes versus small mistakes, you can actually adapt it, because that also depends on how many samples you have, how confident you are in that particular case. Okay, so there are actually quite a bit of active research. Even though gradient descent is a kind of classic method, is widely used in a lot of the kind of neural network, deep learning research, but people are still finding new ways, right, to find better solutions and actually more quickly. Okay. I think we're going to stop here. So that's basically just a way, as we're summarizing, right? We're going to talk about some of the basic concepts. We'll talk about a few methods. Coming up, we're going to talk about evaluation, how you select the model, right? When you have different models, which one's better? And also a few methods to make it even better. Okay, that's all for today. Reminder, homework 3 is due on Thursday, so make sure you finish by that deadline.
Yeah, see you, Ken. Have a good one.
Hi. Yeah.
Sorry, I just have a super quick question. I don't know why I can't find it in my notebook, but
It's okay.
The equation for lift, just for the homework.
Oh, yeah.
I wanted to make sure because
Right,
I
so
was finding some conflicting stuff.
Yeah,
So
P of A union B divided by P of A
of A
and then
times
P of B of B.
B.
Yes. So the
Okay.
main thing here is that A is a set, B is a set. It's a union.
Yeah. Okay. Yeah, I was seeing somewhere this was a subsect,
yeah.
an intersect.
Yeah.
But okay, but
That's
it's
okay, because here we're dealing with item sets, right? We're talking about those items being purchased together, right?
Yeah.
Rather than saying doing A and doing B, and then the intersection means that that's a variable intersection, right? Yeah. So as long as you understand that part, I think we're good. Yeah.
That makes sense. Thank you
Okay.
so much.
Yeah. Sure.